All right, here we go, one take. So make sure you open up your document, the multiple choice document, and follow along. So pause this as you need to. Number 5. They are asking in number 5 for the frequency of the oscillation. If you measure crest to crest, which I think most of you did, 0.15 to 0.8, when you subtract those two, you get the distance from crest to crest, and the x-axis is seconds. So 0.8 minus 0.15, excuse me, is 0.65 seconds for one oscillation. That's a full oscillation. If it takes 6.65 seconds to do an oscillation, you're measuring in seconds, that's period. All right? They're asking for frequency, which is 1 over period. So you just have to ask yourself, is my measurement in seconds or in per second? All right, those are different things. All right, a meter is different than per meter. So this is 0.65 seconds, so it's period. So you have to flip it up inverse, 1 over 0.65. Number 7 is messing around with the experiment. Generally what you want to do, C isn't a terrible answer, but generally, and it says generally repeat the experiment with one thing removed. So you identify the issues. In this case, the 2 issues are there is a string total length and tension. So the problem is the length and the tension. So you get rid of one of them. And so the answer for that one was, let's see. Yeah, it said repeat an experiment with a string that doesn't stretch. So in that case, I'm not changing the length when I put a mass on it. So number 9, excuse me. Oh yeah, so for that one, you're gonna take force over time. So impulse, right? Delta change momentum is force times time. It's a force times time graph. Whenever you see that force times time graph, you should be thinking area under the curve, right? If it's like this, you just want the area under the curve. This particular one, the piece they want is a triangle and then a square. And it's kind of rough, but it's pretty clear that that's what they want. If you look at it again, it's pretty much a triangle and then a square. So you get those two. This one's 10, this one's 20. Now, there is a difficult, there's what they call a distractor, letter D. The magnitude of the change in momentum cannot be determined without knowing the mass of the object. True. I'm sorry, that's not true, but you can't know how much the object's velocity changes without knowing its mass. But you know the impulse applied, and impulse is a change in momentum. So you are hamstrung at the point where they would say, okay, well then how much does its speed change? Well, you gotta tell me how much it weighs. Again, back to my examples from class, you can push Samantha and you can push Karam with the same push, right? There's a change in momentum. I applied 10 newtons for 2 seconds, great, 20. Okay, but Samantha's gonna be moving faster because her lower mass. Does that make sense? I assume so, unless Samantha has gained an enormous amount of weight during our COVID, but I don't think that's true, and I know Karam hasn't lost any. Next one is number 18. Let's see, 18. Oh yeah, block is released from rest. This one is very easily overthought. I stared at it for like a couple minutes trying to figure out if they wanted us to go down a rabbit hole or not. Really, all they're saying is if you break those vectors up, actually I haven't broken it for you. The F and G are opposite, right? But MGH is still MGH. And if the block is sliding, then it's sliding. If there's enough F that it's not moving, then it's static, and that's a whole separate issue. So really what they're asking for is this this horizontal force adds velocity. Not a big fan of that one. I don't like the ones where they just kind of leave it wide open like that. Yeah, I don't think that's a great question. There's a lot better ways to get at that idea, but whatever. Number 20, tree it up, bros. Oh, 26. Oh, 20. Yeah, 20, my bad. 20 is, oh yeah, 20 is good. Remember, this is from a Tippers. This is from our Tippers on, I want to say energy. I think this is from the back of the Tippers on energy where the guy's shooting arrows off buildings. All the V's are equal. You'll see that wordage. Read the question again, and it'll say 3 identical rocks are launched with identical speeds. If all the V's are equal, MGH plus 1/2 mv squared equals 1/2 mv squared. Remember in the beginning of the work and energy unit, I told you that the beauty of it is it lets you bail on all the sine and cosine BS from kinematics, right? This is true. All right, you can't argue with that. By the time it hits the ground, MGH plus 1/2 mv squared, the initial kinetic energy plus potential energy, right, is going to, potential energy gravity, is going to equal my kinetic energy final, right? Initial final. So those have to be true. So all my V's are equal at the end. So rock 1 and 2 have the same initial VYO because rock 1 goes up and back down. After it comes down a little bit on its way down, it looks just like rock 2. It's going down at 45 degrees. And remember, if I throw something up at 10 meters per second, it hits my hand back at 10 meters per second. So rock 1 is identical to rock 2 by the time it passes back down through the plane at which it was released. So 1 is equal to 2. And then 3 doesn't have a VYO. So it's not going to, all of its initial energy is going to be in the X direction. It will be going the same speed, but it won't be split the same way, if that makes sense. All right, 26 is, let's see, wifey's teaching in a couple minutes, so I'm going to wrap this up here. Just tree it up. It's an 8 and a 4, all right? The 8 and the 4 are in parallel pretty clearly, which means if the ammeter is 2 amps, right? So those 2 amps and that 8 ohm make a 16 volt. They're in parallel, so it also has to have 16 volts. Sorry, I was in the way. Also has to have 16 volts. If it has 16 volts and 4 ohms, you know it's 4 amps. They're parallel, so these two sum. The 2 and the 4 sum to a 6. And then if you look at the picture, if that 8 and that 4 parallel, it doesn't even matter. It's like 6 2/3 or something like that. Or I forget what it is. I wrote down the number that it doesn't matter what it parallels to as a resistor. The point is, it's in parallel with, it's in series with R. So because the resistor that those two parallel together is in series with R, it has to have the same current because any two resistors in series have identical currents. So 6 amps. 28. Let's see, 28. Yeah, this one's pretty good, actually. I like that question. That's a reasonable question that gets at some pretty basic ideas. So you can very easily calculate force times radius is torque. 2 newtons, 0.5 gives you 1 newton meter of torque. Brilliant. Torque equals I alpha. So right off the bat, if they say find me alpha, but they don't give you I, you're kind of porked. So then you're thinking D is good. And then you can, okay, well, that's rotational answer. What's my linear answer? Time is 1 second. Initial omega is 0. It started at rest. Final omega, we don't know. Alpha, we already said we don't know. And delta theta, the change in displacement, angular displacement, we don't know. 3 is too many. You can't answer this question with 3 unknowns from a rotational kinematics perspective. So actually, I guess it's not linear. It's more like my linear rotational analogs. So linear, I should probably say rotational kinematics is probably a better way to say that. Rotational kinematics. I just use the linear because it's my analogs. So anyway, it's the kinematics, the rotational kinematics. So either way, it still doesn't work. And then 29, the stick is it's moving counterclockwise initially, and this is my axis of rotation, so that's counterclockwise, right? If it's moving counterclockwise and you apply a clockwise, right? Because this is going to be clockwise, this is going to be counterclockwise, right? So this is helping it, this is hurting it. So sorry, this is speeding it up, this is slowing it down. Drives and fights, essentially, right? The fight, if it's the same F, this fight has a much larger R, which means it is going to be slowing it down, right? So the torque is greater on this than this. Same forces, bigger R means bigger torque. So it's slowing it down, but they say immediately after time t, so it's still moving in the counterclockwise direction, but it is slowing down. Number 30 is 2 systems are in oscillation. So this one's kind of nice. I like this one too. You don't try and like in your head say, oh, it's going to be this. Take your time, right? Period of a spring, period of a pendulum. This is straight from the equation sheet, so they already give you these. M over K, L over G. It's 2 pi rad over 2 pi rad, M over K, 2 pi rad, L over G. So this is the relationships. And we talked about this. A pendulum is not affected by mass. Springs are not affected by length, right? So you read A, increases the mass of the pendulum. There's no M in pendulum, so you cross it out. You read B, increase the angle. I don't see theta in here anyway, so cross it out. C, decrease the mass of the block in the pendulum. Okay, well, I know decreasing the mass of the block, the spring system is going to make a difference, so I put a question mark. D says shorten the pendulum, so I'm changing the length of the pendulum. So that will do something, so question mark. So then we ask ourselves, who has a higher and lower period? My spring has a high period, my pendulum is a low period. If you're not sure why that is, read the question again. So then I say, okay, I look back at my equation. For C, I decrease the mass of my spring system. So for a spring, If I decrease the mass, the period goes down. So for spring, my period goes down. And for D, I shorten the pendulum, which means I shorten this, my period pendulum is going to go down. I have a high period and a low period. I want to bring my spring period down. So it's got to be C. Last two. Sorry, wifey, I'll be out of your way. Don't worry about the air one, 30 and 31. I'll answer them if you're really curious. Or sorry, 31 and 32. I'll answer those if you're really curious later, but that's not on the test because they got rid of it. Hollow plastic ball. Yeah, it's got air resistance. So that's air resistance, AR. I'll just call it AR. Air resistance. It's going up at 45 degrees, so we break it up into components, Y and X. My Y component is gravity, so gravity's pulling it down. My air resistance is fighting, so AR and G. And then you do Pythagorean theorem, A, just according to triangle magic, what we call trigonometry. A, if there is an AR and a G, A will be bigger than G. So A is greater than G and angled in that direction. Last one is 35. 35 is more of a process of elimination than anything. So A is, you got a big charged sphere in the middle, and you got a D, and they want to halve, if you get that L in there for English, halve the force. Bringing it twice as far away will get you F over 4, right? Because it's over, this whole thing is over R squared. It's over R squared when you're doing the forces. So if I double my distance, it's going to have F over 4. That's not what they want. They want F over 2. I look at B. B, they're putting it out at the hypotenuse, which sounds pretty good because I know there's a rad 2 in the hypotenuse. If these are both 1, 1, 1, that's a rad 2. And I square 1.414, I get 2. That looks all right. Let's check the others. C, half of D is going to be 4R. You don't want to get it closer if you're trying to get it less force, right? You get 2 charged particles closer, the force is larger. And D, they're just switching it to the other side, negative. And so, well, actually, I guess they're not going the other side. They're going up in the y-axis. But either way, it doesn't matter. It's still an F. It's either positive or negative. So they put it down, and it doesn't matter. So that's not going to change it. You need to understand that it doesn't matter in which direction it's going, right? It can be right, left, up, down. It doesn't matter. If it's a distance D away, it has the same F, and then you assign components, blah, blah, blah. So clearly B is a good choice then because we know it's not A, it's not C, and it's not D. All right. There you go, kids. That was 12 and a half minutes of your time going on 13. I'll be online Friday at 11 for office hours. Jump in if you want to chat with me about this, or you just want to ask some questions about personal hygiene during a COVID crisis. Love you. Miss you. Bye-bye.